Okay, today we're going to talk about simple gas laws. So the first gas law we'll talk about is what's called Boyles Law. Boyles Law is the pressure volume law. And what it states is that the volume of a given gas, assuming we have constant temperature, varies inversely with the pressure. So volume is inversely related to pressure. Now, there's a constant C here that we're going to use, and that's just kind of a tool to help us better relate the values of pressure and volume that we get, and if the units change and so on, we can account for that by using that constant C. So, if they vary inversely, if you think about what happens here, if the pressure were to increase, that would result in a lower value for volume, right? Because you're dividing by a larger number, that means the overall volume value will go down. So inversely, remember, as one goes up, as one increases, the other decreases. And we've seen inverse relationships before, like with the speed of light. So if we have two scenarios, let's rearrange this. Let's say that volume times pressure is equal to C. I'm just taking the same equation and multiplying both sides by pressure. Now, if there is one instance where this happens, but we set it equal to another instance, say a different volume and different pressure, because they're bound to be the product of P and V have to be equal to the same number, then the C can be dropped out of this equation, and we get what's called Boyles Law with 4 variables. And if you change the volume, the pressure will change accordingly. So you can solve for any one of these. You can solve for the initial pressure, or the new pressure, or the initial volume, or the new volume, as long as you have 3 out of the 4 variables. So let's try this first example. So a 450 milliliter sample, so milliliters is volume, right? So we can call this V1, of helium at 760 torr, okay, so that would be P1, the original pressure, is compressed, so it's squeezed, and the new volume is 200 milliliters, so that's V2. What pressure is needed to do this? Well, notice that I don't have my second pressure, and they're asking for pressure, so we're solving for P2. So if I rearrange that equation that I was given, I can divide both sides by V2, and that allows me to isolate P2 because that's what I'm trying to solve. So I just go ahead and plug in the values that I was given. So the original pressure, 760 torr. The original volume was 450 milliliters, and we're dividing by the new volume, which is 200 milliliters. My milliliters units cancel, and that leaves behind torr, which is okay because that's a unit of pressure. So 760 divided by 760 times 450 divided by 200. 1,710 torr. So another example. If 225 milliliters of helium at 760 torr is given a pressure of 850 torr, what volume? So notice here we're solving for V2. So let's assign what we have. And sometimes this is tricky. You got to take your time and read, make sure you know which was the beginning and which is the final. So 225 milliliters is a V1. 760 is P1. 850 torr is P2, so we need to solve for V2. So no problem. P1, V1, and we're going to divide both sides by P2 because we're trying to find V2. And we plug in the values we have. 760 torr multiplied by 225 milliliters, and we're dividing by 850 torr. The pressure units of torr cancel, leaving us in milliliters. So 760 times 225 divided by 850. 201 milliliters. So that's Boyles Law. Moving on to Charles' Law. So Charles' Law is the temperature volume law. And so similarly, we've got just two variables, and we are assuming that the other variable's pressure is constant. So pressure, or volume and temperature, are proportional. Or directly related. So volume is multiplied by constant times T. That means if T goes up, the volume goes up, right? Directly related or proportional, right? So to put this into a format that can be used when conditions change, you can rearrange this and say, all right, well, V over T is equal to C. And C is a value that will always be true. So if C is always true, then I can take one instance, set it equal to C, but set that equal to another instance, and that gives us V1 over T1 is equal to V2 over T2. This is known as Charles' Law. So the key thing is, remember that any time that you use temperatures, you must convert to Kelvin. So in this problem here, automatically, instinctually, I'm going to take any temperature I see and convert it to Kelvin by adding 273. So 20 degrees plus 273 means this is really 293 Kelvin. 37 plus 293, 273. Let's try that again. Plus 273 is going to be equal to 310. All right, so we have two temperatures. And what would this temperature change do to 1.6 liters of gas? Well, if they're asking what it's going to do to 1.6 liters, what they're really asking is what is the new volume? They're asking for V2. So we'll take the equation, we'll rearrange it for V2. So V1 over T1, multiply both sides by T2, and that's going to let you find V2. So let's plug in what we have. The first volume, 1.6 liters, divided by the first temperature, 293 Kelvin, multiplied by the second temperature, which is 310 Kelvin. So 1.6 times 310 divided by 293, 1.7 liters is the answer. That is the new volume, V2. Okay, let's try the second example. So I have two temperatures. The first thing, let's convert them. So this is going to be 295 Kelvin. Oh, they're asking for the temperature. So T2 is what's being asked. All right, so we'll rearrange the equation to solve for T2. So if V1 over T1 is equal to V2 over T2, hopefully you recall that we don't want to solve for variables in the denominator, right? This is you want to bring it up into the numerator if we're going to be solving for it. So we got a little work to do here. Let's multiply both sides by T2. And what that's going to do, it's going to cancel the T2 on this side. And so now I have T2 in the numerator on the left side. So now I need to get it alone. So I'm going to multiply T1 to both sides, and that will get rid of it on the left side. So T1 goes up here. T1 going up here will cancel the T1. And so one more step. We want to get rid of the V1, so let's divide both sides by V1. And this will then simplify to be T2 is equal to, well, what's left? is equal to V2 times T1 over V1. So don't solve for variables in the denominator. You have to get them up into the numerator and isolate them. Now that I have my equation set up correctly, we plug in what we know. So V2, the new volume. All right, so which one was the new volume? V2, that was the new volume, this was the old volume. So 225 milliliters times the first temperature, 295 Kelvin, over the first volume, which was 21. All right, my units for volume cancel, meaning my answer is just going to be in Kelvin, which makes sense because we're asking for temperature. So 225 times 295 divided by 21. It's going to be pretty warm, 3,161 Kelvin. All right. Gay-Lussac law, or the pressure-temperature relationship, is very similar. And so the derivation is going to be basically the same as what we did before. So if pressure is proportional to temperature, then pressure over temperature is equal to a constant, and that means P1 over T1 is equal to P2 over T2. Now, if I'm using this equation, that is assuming the other variables are constant, like volume. So we could go ahead and solve for examples like this, but what you might realize is then these relationships are very similar. We can just combine them into one and use what's called the combined gas law. All right, the combined gas law combines pressure, temperature, and volume all into one convenient law. And so when you're using the combined gas law, P1 V1 over T1 equals P2 V2 over T2, you can use this in any one of those scenarios that we mentioned earlier. So I could use this law in the first example and the second example that I did, because if a volume is not mentioned, I can just go ahead and ignore the volume, right? I can kind of scratch it out and look what happens. If I ignore the volume, then really what I have then is pressure over temperature. Or if I have another law and they don't mention any temperature change, then I ignore the temperature changes, and then we get Boyles Law. So the combined gas law is really like a multi-purpose law. You can use it in any scenario. Just know that if a variable is not mentioned, you just ignore it. Okay, so let's try this last example here. 120 milliliters. So I'm going to go out on a limb and call that V, that's a volume, that's V1, of argon at 780 torrs, that's P1, that's our first pressure, and 32 degrees Celsius. Now 32 degrees is T1, but it's not going to do us any good in Celsius, so we add 273 to that and we get 305. Then we change the conditions. So we are changing the pressure. So this is now P2, and this is now V2. And they're asking for the new temperature. So they're asking for T2. So we need to rearrange our combined gas law to solve for T2. So if this is our combined gas law, and I want to find T2, then I can go through and do the steps manually, but a little trick is these two will flip places, giving me T2 is equal to P2 times V2 over P1 times V1, and then I just multiply both sides by the T1. So I was able to quickly manipulate that law because I knew what the outcome would be. I knew that the T2 and the P1 V1 by cross multiplying would eventually just switch places. So let's plug in what we know. Let's take the second pressure, which is 750 torr, multiply it by the second volume, which is 250 milliliters, multiply it by the first temperature, 305 Kelvin, and then we're dividing by the original pressure, and also dividing by the original volume. So 750 times 250 times 305 divided by 780 divided by 120. And so our answer is 611 Kelvin. All right.